professor at the Centre for Memory and Brain of Boston University and co-founder of the Neuroengineering Corporation of Massachusetts. He established the minduploading.org website and first proposed a team and science-specific approach called whole brain emulation. The purpose of which is the technological accomplishment of mind transfer to a different substrate. Okay. Thank you very much, Randal. Put your hands together.
Wow, that was the longest introduction I've ever had, I think. So first of all, I'd like to apologize quickly to anyone who was at the talk yesterday at Embodied Books, because this is basically the same topic, except I've got more time, so I'll be a little bit slower. Yeah, so what I'm going to be talking about is this idea of substrate-independent minds, or SIM. And the way that I usually start is that I try to explain something about my motivations. So something about what is behind all this stuff. Why would you want to do anything like this? And then I explain what it is and where we are right now in getting there. So my take on it is this. We're all traveling into the future, as are our children and our grandchildren. And so really it's relevant to all of us how that future turns out. And when we have a really good future, we tend to call that a utopia. Well, at least that's the most ideal future we can think of. It's a future in which our species thrives. When we have a bad future, we call that a dystopia. And we've got some agency in this matter, because right now, we've got something such as a global infrastructure, a global economy, and global science that we can direct at the problems that we choose. So I think you all know what I mean when I talk about a dystopia. There are so many examples. Science fiction is full of them, in movies and books. Some of them are about scenarios in which the entire population ceases to exist. And I think it's fair to say that even now, some people in various parts of the world are living in circumstances that we might call a type of dystopia. So this idea that humanity will disappear through some sort of event that we cause, through an environmental disaster, perhaps through plague, war, or, I don't know, robot uprisings, even a large meteor impact. It's a very common idea. It's been around since Revelation and in modern pop culture as well. Some people are saying that 2012 is the year where things are going to happen. So this has been going on for a while. But we can also imagine a dystopia where, sure, it doesn't mean everything ceases to exist. It's just that civilization doesn't work the way we're used to it. Something breaks down. You know, we don't want to be treated like objects or resources. Imagine just a future in which everything is completely corporate. And we're almost there, so dystopia may be just around the corner. So what is it about a civilization that separates us from dystopia? Let's begin with the concept of evolution. This is the consequence of selection, really. That's what I'm trying to display here. It's a very important concept because it's been going on forever. It's been going on throughout the past, and it will continue to shape the future as well. It's everywhere, too. Daniel Dennett described this as universal Darwinism. So it's not limited or constrained to living things either. Selection is taking place everywhere all the time. We could consider, for example, a collision between a large porous asteroid and a small dense one. And we could say that the outcome will select for the smaller dense objects that are going to continue to exist for a longer period of time in a much larger space. I'm going to get back to this in a moment, when we have to ask ourselves what sort of long-term selection pressure affects an intelligent species. Our natural evolution enabled us to develop better ways to communicate with one another, to interact. And with that, we build societies and cultures. A civilization is a means to support human interests that go beyond raw competition, such as trying to understand more or trying to create more. Sometimes creation is just about making things that enrich our experience in an aesthetic way. Civilization, in other words, is a catch-all for our ability to harness cooperation. Another facet is empathy. With better empathic abilities, cultures and civilizations move from cooperation that is achieved by a hierarchical coercion to one that's more through empathic cooperation, meaning you can understand other people and why they want things done in a certain way. And I'm sure you've noticed this when you look at politics, that there's this difference. Happens to be an election year in the US, so in the US at least, we see all of this become very explicit. You'll see some people that emphasize the importance and value of hard work and competitiveness. And then you'll see other people emphasizing the importance and value of empathy and of compassion, that when you apply it properly to those who are in need, can lift up all of society. And I think together, cooperation and empathy lead to what we know as ethics. So those are about having respect for the value of differences, in fact. Different groups, different individuals, and different goals. We all like to belong, so we all like to feel enjoyment and comfort and strength in those things that we have in common. It's a really important thing about how we fall in love, how we create families, how we choose interest groups, and even nations. But at the same time, all of us want to be respected for our own backgrounds and insights and our creations. So we're trying to protect these minority interests of ours from the tyranny of uniform majority. And in fact, when we think again about what we want from civilization and what separates us from a dystopia, one of those things is to keep us away from a machine-like uniformity. Imagine considering a system or a computer brain that is good enough or considered good enough or superior to us and creating millions of copies of those. Even there, we often see this sort of dystopic idea, in that case not because we're all being destroyed or something like that, but simply because it's uniform, it's all considered better than the strange differences that we're all coming up with. So that could also be a dystopia. But evolution takes place in a specific environment and at a certain time, in an epoch. That means that natural selection led to us being suitable to the environment and the challenges of a certain place and time. But things change. We know that one day the Earth is not going to be a shelter for humanity anymore. That could happen soon by our own hand, or at the latest, when the sun's atmosphere expands and engulfs the Earth. It would be difficult for us to move elsewhere if we have to take a replica of Earth with us wherever we go. In fact, you could say that Neil Armstrong never really managed to touch and experience the moon because he had to be encased in a suit of Earth's atmosphere, inhaling his own scents. It's also not optimal to have senses and thinking that are selected for survival problems that you faced millions of years ago. So let's revisit universal Darwinism again, the big picture. What sort of intelligence, what sort of culture would be good for inhabiting and influencing the most of universal space-time? When we adapt our bodies, we're able to inhabit and influence all of Earth. This has happened already. The clothes that you're wearing, the houses you live in, the cars you drive, the cell phones you have. So, similarly, we could say that the most adaptable are going to inhabit and influence most of everything that will ever be. Now, this is not a very strange concept to us at all. I just mentioned all those things that we already have that are augmenting us. I think you could say that to be human is to be augmented, so there's really nothing unnatural about that. And it's what we learn and what we teach our children, is to try to augment and to be able to adapt. Consider, for example, when you first learn to drive a car. A car is much faster and stronger than you are, but still, after a little while, it becomes your own, and it begins to feel normal to delicately weave through complex traffic situations. So far, the way our minds have coped is by sharing burdens. We specialized, and we became ever more dependent on each other. We used computing tools for those things that we're not so good at. We used networks like the internet to speed up and to add ever more information. And in school, I remember that we used to learn historical facts. We used to learn things about society as items that we needed to remember. Now, we don't do that anymore. We just have to become better at asking the right questions when we Google something or when we look something up on Wikipedia. So we already see a change here. In fact, we're offloading most of these simple computations, most of that data gathering, to other types of tools that do this better, to databases. And especially, therefore, we rely explicitly on external memory. At the same time, we're living longer and we're experiencing more. But what does that really mean? We have to ask ourselves, what does it mean that you can live longer and experience more? Who are you? What are you? What is a personal identity or a self? And correspondingly, what is everything else? You experience yourself sitting here. You experience yourself listening to me. You feel the seat. You hear and you see me. But really, those things are already things that have been generated, that are processed. There's nothing original, so nothing that's just pure about that. Everything you experience, everything that you're thinking, remembering, your concept of what's going on around you, where you are, when you are, all of that is generated by mental processing. Without it, there's nothing. And that processing is really all there is to being. Some say that the self is an illusion, but everything else is just as much an illusion in the sense that it's all a construct, all a way of structuring things, a way of labeling them and constraining the patterns of your mental activity. We need to understand this aspect more so that we can be more enlightened and go for better things instead of strife. We don't want to fight and harm our friends because we tend to understand them better. We have more in common. We feel kinship. And as we learn to understand being more, that's how our civilization matures. Now, all this processing, there's really no reason why it should be unique to one implementation, the human brain. It could be done in many different substrates. That's where the solution really lies to adaptability. It's about achieving functions of the mind in different substrates. And, okay, so this is, how do I compare that? So different substrates, it's kind of like, say if you work on software, I don't know how many of you understand a lot about software, but it runs on a certain platform. Let's say you've got software that runs on a PC, or it runs in a certain software language. If you can make it run on another platform, it becomes platform independent. And that's the same idea here with substrate independence for minds. It doesn't mean you don't have one, you don't need something to run on, but it can run on many different types of substrates. Imagine what it would be like if you could augment yourself so that you could have memory like a computer database, as precise as that, or if you could find optimal solutions with the comparative ease of, say, a quantum computer. Now, what we see here is that we've gone on from the simple idea of how do you get to substrate-independent minds to an actual roadmap. And how did that come about? It comes about just by looking at what would be feasible today. If we want to understand how to create a mind in another substrate, you could go about it in many different ways, but we don't really understand enough about the mind to take the most optimal route, which would be the one where we really understand all of the strategies that the mind is using at the top level, right down to the cellular level, and implement that in the best way possible for some other hardware. What we do have some grasp on is the lowest level. Neurons, synapses, how do you measure things there? That's the kind of stuff that neuroscience has been doing for the last 100 years. And working at that level, we call this whole brain emulation. The idea that you take all of that physiology, all of the anatomy, you break it down, you try to understand that and replicate it. And this leads to a simple roadmap, which I'm going to describe in some detail. So it's really up to us to decide if we want to achieve something like this and be able to transcend into various different types of challenges and environments. And we can take advantage of the fact that right now we have so much at our disposal. That's why I think this is a valid thing to go after right now. Now, anytime you're trying to do some kind of emulation, whole brain emulation or emulation of a small system, or whenever reconstructions are done in engineering sciences or in exact sciences in general, what you're really doing is something called system identification. It means that you're looking at an unknown system, a black box. You know that it receives certain types of inputs, and you know that it produces certain kinds of output, and there's usually a correlation between the two. And you need to understand what the functions are that carry out that process. Before you can do that, first you need to understand what are the important behaviors, the effects, and then the signals that you're interested in. If you think, for example, about trying to analyze an unknown microprocessor, you've got a chip in front of you that belongs in a PC or in some computer, and you want to understand what it does. you could look at all sorts of signals. Now, we happen to know that what it's actually processing are these voltages that are thresholded, and they can either represent a 1 or a 0. That's the binary format. And that's what you're trying to understand. How are these binary inputs turned into those binary outputs? But of course, there are many other signals you could look at. You could look at air pressure. You could look at temperature that's affecting the chip or that the chip is generating. You could look at cosmic radiation, all sorts of other influences that are there. And the same thing is true when you're thinking about system identification in brains, in neural circuitry. Again, you have to consider what sort of signals are there and which ones are the most interesting ones, the ones you want to start with when you first come up with your first iteration of a model, and then you want to see if that model suits the effects you're trying to capture, and if it doesn't, you need to add something more. It's an iterative process. Now, there are some things that lead us to believe that a good level to look at in the brain is at the level of the timing of what we call spikes, action potentials of neurons. The reason is this. What sort of effects are we interested in? We're interested in all kinds of cognitive functions, like perception. And these functions all seem to be driven by those spikes, by spike timing. Sensory input through our cochlea, sensory input that we hear, sensory input through the eyes, the retina, all of that gets turned into trains of these spikes, of these action potentials. And it's the timing of those spikes, the rates of those spikes, that is important. Similarly, when I'm speaking to you here, I'm using my vocal cords. Those are all muscles. They're driven by muscles. And muscles are driven, again, by a certain rate of spiking. So again, it's this spiking that seems to be important. Similarly, when we look inside the brain and we think about learning and memory, it so happens that the way synapses change their strength depends critically on the timing of this spiking, on spiking at the neuron that is before the synapse, the presynaptic neuron, and spiking at the postsynaptic neuron. The order is important, and the difference between the spikes, what the timing is. So it seems if we could make something that properly predicts spike timing, then we may have a good emulator. That's a good place to start anyways. Now, there are quite a few things in this roadmap that still need to be addressed more carefully. There are some gaps there. But luckily, most of the problems that we're facing are already being tackled by some groups, some projects that we have. And this is just a slide popping up a few of the people that have been working on this for the last few years. Many, many more have been added recently, so it's quite good to see this. I'm going to take you through a few as we go through this, through the rest of the presentation. Now, in this roadmap, there are really four major parts that need to be looked at, and I'm going to take you through them one by one. There's what I call scope, resolution, then there's the matter of, it's on the right here, the emulation platform, and then the structural connectome and functional connectome, or functional characterization as I like to call it. And on the bottom you see a few of the projects that are being done to work on those. Not all of them, this is a bit of an overslide. So, the first problem that you need to deal with and requirement in the roadmap is you need to understand how big is this black box that we're trying to define? What is the scope of this thing? And it's not just a question of do you look at the cortex, do you look at the cortex and the spinal column, etc., but it's a matter of how big of a black box can you handle? What can you describe? Because if we take the entire brain and you're trying to describe the functions that are in there, trying to learn about them just by looking at input and output, for something with 100 billion neurons and trillions of synapses, if you wanted to describe the functions, you would probably have to observe the behavior of the brain over its entire lifespan. And even then, you'd probably have a flawed representation, and you'd be missing latent function. So parts of that brain that were already instilled, say, for example, during your development stage, and how that affects your future learning and the way that you're processing patterns. So really, well, the more we know about the input-output and the more we know about the architecture, the better we can break this down into smaller problems. And that makes it easier to manage. We'd like to deal with small system identification problems, little black boxes that are all connected to one another, and we need to know how they're connected. That's the way to handle this in a feasible way. The second big problem that needs to be dealt with is, of course, that if you're going to emulate something, you need a platform to emulate it on. So what kind of a platform would that be? What would it need to be able to do? Well, first of all, I'm going to make an assumption about how we're going to model things on there. Let's say that we break down this big system identification problem into what you see here, which is a representation of a neuron with all sorts of little pieces that represent the dendrites, these connections that go between neurons. And the dendrites are represented as little cylinders. Each cylinder has an equivalent that is like a little electrical circuit, and you use something called the Hodgkin-Huxley equations to describe how it deals with the responses that are going through there. So this is a well-known method of modeling in computational neuroscience. We could assume that maybe there are 10,000 of those compartments to describe one neuron. So this gives us some idea of the scale. And now how much is going on at each one of these neurons? Well, one way we can look at this is by looking at the energies that's being consumed. Our brains take about 20 to 40 watts, so it's about the same as a light bulb. Every single action potential, every spike at a neuron, takes a certain amount of energy to be produced and to be pushed out, all its effects being pushed out to its neighbors. And that takes about 80 million ATP. ATP is an energy unit in biology. If we convert all of this and we look at what's going on in the brain, and we take into account the fact that we have 10,000 compartments here, I'm not going to take you through the whole calculation, but it turns out that you need a computer, if we were to use a regular computer, that could take care of 1 exaflop in computation. Now, a regular PC does gigaflops nowadays. Then you can go to teraflops, petaflops, and even petaflops are not sufficient, and that's where our current supercomputers are. Supercomputers are about 10 petaflops. That's the fastest computer right now. It's 100 times too slow for an emulation like that. But if you look at the plans that are out there right now, by about 2017 to 2020, the US, Japan, and even India are going to have exaflop computing. So even if we didn't try to tune our hardware to the problem, there would be computing power available to do this. Although better, you'd use some hardware that is better suited to the problem. And again, there are projects that are dealing with that. For example, DARPA has a project called Synapse, which is building neuromorphic chips. So I can imagine that there are much better solutions than that. But we can already see that the biggest hurdle here isn't going to be the amount of computation that you need to do. The biggest hurdle really is acquiring the data from the brain that you need to build up these models. So we needed to break it down into smaller problems. That means we need to understand how all these little problems, these tiny black boxes, how they communicate with one another. That's what we call the structural connectome. How are all these things connected in the brain? How are all the neurons connected? The problem of getting the structural connectome of a brain has become really interesting in neuroscience over the past few years. It started about 2008 that it became a really interesting problem. And there are many groups that are working on it in different ways. Last year, we had some really interesting results. 2 groups that are both working together with Winfried Denk, who's at the Max Planck Institute, did some wonderful work where they took electron microscope images of slices of brain tissue and used it to reconstruct pieces of the brain in 3D, and from that predict the function of what was underlying that. And the 2 pieces they looked at is the retina in one case. So the retina is actually considered part of the brain. It's the most external part of the brain that we have. And the visual system, there's in the visual cortex. These are really proofs of concept that the kind of emulation from reconstruction that we're talking about are possible in principle. Now there are, let's see if this is going to work. Yeah, here you see some of these slices being stacked together and using them to reconstruct circuitry. This is actually a movie that I got from a friend of mine called Ken Hayworth, who works at Genelia Farms now. He's another one of those people who's working on tools to quickly scan slices of brain tissue. He's working on a new tool called a focused ion beam, SEM, using that for this kind of reconstruction to speed it up, because the big problem is really not the resolution. The resolution's great. You can see individual synapses with that. It's the volume, trying to deal with something the size of even a small brain. Let's say at Genelia Farms, they want to work on Drosophila brains. Those are the little flies. It takes a lot to get there. But when you do, you can reconstruct something like this, where you can see the individual neurons reconstructed. The red thing here is a piece of vasculature. That's blood. And the green, purple, and yellow, those are 3 different cells. You see some dendrites and axons of those there. And if you were to look very carefully, you could probably find a few places where they meet, where there are synapses between them. This is actually not a very high resolution image you're seeing here, so this isn't giving you the best information that you could pull out of there.
If I can interrupt, how many neurons there?
How many neurons in this picture or in... Well, these were three. We had the three different colors were displayed there.
Right.
Yeah. But even if you get all of that, you still don't know as much as you need to know to make a good emulation, because you can maybe understand something about the type of neuron you're looking at, because every neuron has a certain shape. So you'll know if it tends to be an excitatory neuron or an inhibitory neuron, something that decreases activity, just from looking at the shape. So it tells you something about constraints you can put on the model. But it doesn't give you all the information about the channels in the synapses and that sort of detail. Really, you need more information to constrain those little black boxes you're dealing with and fill in the parameters. And that's the work of getting functional characterization. And now I don't know why this is cut off on the top there. Maybe this is because in an earlier, I don't know, maybe this was moved or something. There's some kind of issue. Doesn't really matter. This is just giving you some examples of work that was done by, for example, Eugene Itzkevich in coming up with a good model that can characterize the functions of various different types of neurons and how people go about doing that in the neurons of different parts of the brain. One of the big problems we have here is that the real tools that we need aren't available yet. So in functional characterization, I'll explain this in a second, right now all we have is either you stick a big electrode in the brain and you can look at a few points and get some detailed information at high-res temporal resolution out of that. Or you can look at the brain in a very low-res way, like an MRI, magnetic resonance imaging, and you can see some of the activity or differentials in activity. But it's not good enough to try to populate the kinds of models at the scale I was just showing you there. Now some attempts are going into making arrays of electrodes, lots of electrodes, 10,000 electrodes, and sticking them into a brain. But you can imagine what kind of a pincushion that becomes, and that's interfering with what's going on in there. The same happens if you try to pump up the power of something like an MRI. If you're doing external imaging and you try to get down to very high resolution, physics can tell you right away that getting to a higher resolution is going to require more power. The more power you're putting in, the more you're going to interfere with what's going on in there. So now you're not just measuring, you're affecting the system, and in fact you're going to kill it too with that kind of power. So that's not ideal. But there are some other solutions. The brain uses a completely different way of getting at information at high resolution inside itself. And it does that at huge quantities as well. And how does it do it? Well, that's where those synapses come in. All of those synapses are really little measurement devices. They have channels that record something. So the trick is to be small and plentiful. Now, one way to do that is through this approach. It's called the molecular ticker tape. It's a collaboration that's currently going on between Harvard, MIT, and Northwestern University, and is producing the first results right now. The idea is that you can have a piece of artificial DNA that's being amplified. They've been stuffed inside every neuron. They're being amplified, meaning they're growing and they're always repeating the same sequence. But there's also a channel that is voltage sensitive, so it can sense when the neuron's becoming active. And every time there's activity, the amplification makes errors, makes more errors. So you can see approximately what the voltage is by looking at the error rate on this tape. So all you do then is you get in there. All of these neurons have been populated with those tapes using, for example, a virus to deliver them. And then you take out those DNA strands, you look at what's there, and you have a synchronous measurement of the activity across all of the neurons in that piece of tissue. It's not been done, I mean, it hasn't been tested yet, but the DNA ticker tapes, those molecular ticker tapes are now being produced, and the first tests have started, so that should be really interesting. Another way to go about it is to use something called functionalized nanoparticles. A well-known type is the Q dot. Many others are being developed as well these days. So this is basically the idea that you can use a small particle to amplify the activities there such that it does become visible to imaging procedures that you would use outside the brain. The results, I don't know of any yet that have really made a huge impact, at least not at the level of large volumes of tissue, but I think that in the next few years we will see some. Here's a different approach that I'm personally involved in. It's the use of wireless microprobes. These are not nanoscale, they're microscale. The idea of using very small probes, so getting away from large electrodes, but using just basically the tips of the electrodes, has been tested, at least in theory, by a group that was inserting microchips inside living cells and showed that both the microchip and the cell continued to operate as they should. And these chips were at the size of a micron, so they really were micro probes. The type of cell that we're really trying to produce, I call it a cell, I mean an agent, I call them cyber cells, so it gets a little confusing because cell, biological cell, cyber cell, all the same. They're composed of a small microchip. They are at the size of a red blood cell, so they're about 8 micron in size. At 8 micron, the number of transistors you can put on there is about the same as in the old guidance system for cruise missiles, so it's not that bad. They can be powered by inductive power or through the distribution of power at infrared radiation, because there's a nice window between 800 nanometers and 1000 nanometers wavelength where tissue in the brain is basically transparent to infrared. And you can also use glucose fuel cells. Here the idea is that you put those inside something like a silicon droplet or a protein shell so that they are biologically compatible, and you can distribute them throughout the system. Each of the agents does very little, has only a very specific task, but you use many of them together to do different things, and they're at different scales. So the large one, for example, can be very good for collecting information from the small ones and delivering it out, making it visible or providing power, and others are used to do things like simply detect a voltage. The advantage of using this technology is, of course, that integrated circuit technology is something that's currently quite advanced, and we know how to do it. We can make very many of them. It's not something that lies outside the scope of current technology. It's not so much a science project as it is a project of integrating a lot of technologies that already exist. Okay, let's go on from that. Yeah, so it's a team approach. I already explained that. Now, I think what we really need to understand about this is that we have an opportunity right now. These are all very ambitious projects. This is something that takes an effort. It's not necessarily more ambitious than many of the other large projects out there. Say, putting something on Mars and having a rover run around isn't necessarily much cheaper or easier than doing this. I think the scales are, maybe there's a factor of 10 difference somewhere, but it's a pretty ambitious project. But we do have the means to do it right now. We've got all that infrastructure at our disposal, and we've got the economy at our disposal. The question is, if we were to wait, if we say, looked at this again in 10, 20, 40 years, we don't know if we'd have that opportunity. So it's very important to deal with it right now, just because this does have an impact on our own adaptability, on things that we can do in the future. Now, there is a congress coming up that's sponsored by the Foundation 2045, which is, by the way, also the foundation that is currently sponsoring carboncopies.org, which is my organization for doing all this road mapping and bringing together things that's going on in the various projects. And its topic is exactly that. It's what is the global future for our species? How can we develop further? Where are we going with this? And it's going to bring together leaders from many different fields and scientists that are working either on the body problem or the brain problem, and trying to make sure that we have support systems in place for them. So come up with the ways to fund this, get entrepreneurs involved. It's related to the project called the Avatar Project. It's run by the Foundation 2045 that has several phases that are involved in body and brain issues. And we hope that when we go forward with this, that the interest as well as the input that's coming into this whole project is increased exponentially. And I think after doing this blatant advertising for the next Congress, I'll leave it at that and take your questions. Thank you very much.
Quantum computing, the advent of quantum computing help this exercise?
I'm sorry, does it help the exercise?
Yeah, I mean, you're talking about
it may. It depends. I mean, when people talk about quantum computing in this context, often there are questions like, do you think that you need quantum computation in the brain? So this I'm going to put aside for the moment because I don't see that that's an issue. But quantum computers can help you, for example, to more quickly find optimal solutions in big computational problems. It depends a little bit on how they're set up. I happen to know a bit about one particular company called D-Wave that's producing a quantum computing device that is meant to do exactly that. That helps to pick suitable parameters by basically just settling into a good solution. And I think that quantum computers can be very useful for that, for large parameter optimization problems. Still, even with quantum computers, I think you need to break the problem down into very small pieces to make it feasible. Yes?
Between now and 2045 or whenever these technologies will be available, a lot of people are going to die and be lost to us. Is there the prospect in these various scanning technologies to develop something like a virtual cryogenics facility where you can basically store the connectomes of people for the future when they can be reactivated?
Well, my take on it is that, so anything you try to store some of the information about you is probably better than nothing, right? Because it gives you more than a 0% chance that what is you may be able to be reconstituted. Now, I think that to really do whole brain emulation, as I showed, because it's a system identification problem, you need both structure and function. So you need these tools that can acquire all that data. Those tools are being developed right now. I think that being able to capture enough structural and functional data from the brain so that probably you have the information you need to create something ultimately that would work, maybe finished or maybe doable, at least in the lab in the next 10 years or so. Then you'll have the tools, and perhaps it'll still be very expensive and very difficult, and you can only do this with flies at that point. So then there's another step involved in making volume accessible and being able to handle human brains. But I think if you can hang on for 20 years, then probably the tools that you need to get the data out at least, they'll be there. Putting it all back together and making something that can run in real time and feels like you may take a little more time, but as you said, in that case, you can store that. There are a few other philosophical issues there, because some people worry about things like self-continuity and whether or not being turned off and then being turned on again is an issue. Some people think it's a problem, some people don't. Personally, I'm a fence sitter, so I always argue the opposite side, whatever someone's saying. In that case, maybe the solution of just getting the data out first, waiting, and eventually recreating something isn't perfect. But still, it's better than nothing. So, yeah. I was going for the, right.
The size of your little probes seems kind of big. The extracellular space is large, it's mostly about 20 to 60 nanometers across. And through the channels surrounding the astrocytes and the neurons, you get up to about 100 nanometers. Now you're talking about a probe which I saw a little sign down the bottom that said it's going to go into the extracellular space.
Yeah. Yeah, that's right. I forgot to mention that. So the largest size is the 8 micron cells, which are at the red blood cell size. Right. Those are the big hubs that I was showing, basically.
Yeah.
But there is a plan, in fact, to go to much smaller sizes, and then you have the ability to combine different technologies, such as using the nanoparticles to get information that is required at a smaller scale, or using voltage-sensitive dyes to basically paint what's going on in cells and watch that with an optical way of recording on these cells. All of the solutions ultimately are a matter of combining different technologies. And this is also true for delivery methods, for example. So you can think of one delivery method as having things actually circulate in the blood or in the cerebrospinal fluid, but you could also have delivery methods such as injection, for example, into a specific place. The real problem of getting a tool that works is, again, it's like an iterative issue. You try to build something that works a little better than what we have now, and then you keep going until you've got the full solution. But it means that you have to explore a number of different ways, a number of different solution possibilities, and then combine the best of what you've got to make something feasible that also achieves the ultimate goal. So I agree with you, yes, the spaces are small.
The one you mentioned, good for blood vessels, but the extracellular space is no way to be.
It depends which extracellular space. I mean, there's some places indeed where it's really tiny, where it's small, and there are some channels that are larger. So it depends where you're trying to aim for, yeah. Yeah.
Can you plastinate my brain without killing me?
That was exactly what I was just trying to address with that self-continuity issue, right? Some people would say that if you were to die and your brain were plastinated or frozen, and it contained all the ultrastructure that you needed to get a scan out of it, and you somehow also got the functional information so that you'd be able to create an emulation, that if you were recreated, or even if you were somehow brought back to life through some other method, that you would never have died in the first place. So it's as if you died, but death isn't really, a permanent state. It could be something temporary. That's what some people say. And others say, well, if you die, if something else appears that has your memories and your experience and feels like it's you, it doesn't mean you didn't actually die. You can't just transfer like that. So there's this issue of what do you personally, what's your philosophy on what it means to survive this? It's a philosophical problem. The interesting thing about this is that it could become a practical issue to explore rather than a philosophical problem.
What if I was still alive, though?
What if you were still alive when?
When the plastination procedure was happening.
You'd be dead.
I don't know what to say about that. I mean, a piece of plastic on a shelf to me is not something living. So you could be alive before the procedure and you might be alive again afterwards when something gets created, but you can't be alive while it's sitting on the shelf.
But it's like that movie with Arnold Schwarzenegger in it, where they took his whole memory, made a clone of him, and turned out two Arnold Schwarzeneggers. It's like that.
So you're talking now about a situation where you're kept alive and you create a copy, right?
Yeah.
Yeah, okay, that's what you mean. Yeah, that's the other interesting point. I mean, if your philosophy is that self-continuity isn't really a problem, then sure, you can make a clone like that, and they would both be you, and they, of course, become different people after a short period of time. If you believe that self-continuity is a problem, then they might not be the same person, but you could still come up with procedures in which you could duplicate by, let's say, for example, this is a little bit, it requires extra technology that wasn't even mentioned here. If you could put in place, replace each of the cells individually and gradually replace each one. It's like the ship of Theseus thing, where you replace every one of the planks one at a time. Well, you'd never really disappear, right? A different one would appear. But now what if you didn't replace the neurons, but you just made copies of each one of them? You had duplicate networks that were all running simultaneously, nothing ever stopped. Well, yeah, they'd both be you. Huh. What can you say?
A lot of people who think about generalized artificial intelligence worry that it could be a disaster if it actually happened or we didn't prepare for it properly. Is that the same risk here with uploaded humans? Would it be good for humanity or bad?
My take on it is that it's good, and I think I tried to lay that out in the beginning part of the talk, where I was talking about the challenges that we might face that are different than the ones that we were selected for at the moment. So I think that at some point you simply cannot continue to just manage by being perfectly selected for one environment and one time. So at some point you need to think about moving on, some kind of adaptability, something changes. Now, whether that has the same dangers as what they talk about in AGI, well, there are two big questions there. First of all, is the danger with AGI really as big as some people claim? Maybe it is, maybe it isn't. I'm not entirely convinced yet because there are often not so many discussions about resource requirements, for example, and other things physical things that inhibit a device no matter how intelligent it is. So the explosive, immediate takeover of everything may be somewhat limited. So I don't know if it's as big a problem. That's one thing. The other is that, there is a difference between these two situations in the sense that here we start with a core where you can at least say, okay, this is pretty much us. It's ourselves. So even if it changes, even if it becomes something else, that's still us. Now, whether you then have some kind of a super powerful uploaded human versus a bunch of people who chose not to do this, and if that's the same critical problem there as an AGI would pose, maybe it would. I just think that ultimately you need to face these questions anyway, so you're going to have to go one route or another, and I think that if we can actually adopt some of the capabilities that we think AGI would have, that this would be a benefit to us instead of being bystanders who just see this happening, who just watch technology become ever better at everything we do without really being able to take advantage of those improvements ourselves. Up there.
Yes.
Yeah.
I was wondering, what level of detail do you think we'll need to simulate the brain to get the sort of function that we're interested in? Like, do we just need electrophysiology, or do we need to go down to ion channels or proteins, or what do you think?
So, again, as with system identification all the time, it's an iterative problem. You have to start with a representation or a model somewhere. And what you do first is you try to look at what seems to be the most significant signal you're interested in for the significant effect or behavior you're interested in. And when we look at that and we try to work with the simplest system that we could start implementing, it looks like what we need to capture in the physiological realm is things like the characteristic spiking. What is the shape of the response? How is it being distributed from one cell to another? And on the structural realm, well, we need to be able to break it apart into these small pieces where you can capture that kind of data. So that may be the resolution that's sufficient. Now, the ion channels, either you could describe them by having measured the response from one cell to another and knowing as a global thing, basically, what is the connectivity between it, how do they respond to one another, these cells. Or you might want to measure specifically what are each of those ion channels, what are the types. And for example, in the technology that's currently being used to make those electron micrographs, to make those stacks of images, one of the groups working on this project is also working to incorporate the ability to detect smaller details, like to use protein identification to find out more information about what kind of cell is there. And similarly, you could do something to identify what type of ion channels are there. So you could get at more detailed information, and you would incorporate this in the models if it turns out that you need it. So you look at your model, you find out what works, what doesn't work, and then you improve it by adding more signals or by adding more complexity as required. You don't try to make it too complex to begin with, of course. Yes?
If you have one brain and copy and replicate it from two different technologies, do you end up with the same brain or are they different?
Replicate it with two different technologies. You mean different kinds of solutions for... Well, my guess is that unless all of these technologies were aimed at capturing the same signals at the same sample rate, let's just say, then yes, it would be different, because apparently they would have chosen different most significant things to aim for in their priority list of what belongs in a model. Now, if it so happens that the things that they're looking at are either cause and effect of one another, so let's say, for example, that it turns out that electric fields are really important, but that the spiking in the cell is the one causing the electric field, and that you can compute what the electric field is going to look like from knowing where what the spiking is that's happening, and you know something about the cell, then maybe the two can come up with the same result, even if they're measuring different things. If one of them is measuring the electric field directly, and the other is only measuring when spikes are happening, maybe it would end up being the same thing. But it does depend on how you put it together and what information you're actually collecting. So my guess is in most cases there would be at least some slight difference. Any more questions?
Can you give us any estimation right now on how much space would be needed to store all the data of the human brain enough to simulate it?
Of course, that depends on the technology you're using for that sort of storage. If we're talking about hard disks today, quite a few, I think. I can't say that I ever really thought of the volume as such. Somehow that didn't bother me as much as the question of how much computation you would need. That's why I ran through that calculation. But then ultimately, of course, there's no real reason why we wouldn't be able to engineer something that is computational and able to handle the computations necessary in the brain at the same scale that the brain does it. I mean, we know that this is possible, right? So ultimately, that size has got to be doable. Yes?
So let's say we've got everything there is to know about someone's brain and we're simulating it. Do you see any problems with actually getting like a spark of consciousness?
Yeah, well, all of these questions are really addressing basic questions in neuroscience and psychology that we don't really understand fully. This is about this whole issue that I was saying where we don't really understand from the top level down to the cellular level how it all fits together and what are all the strategies that make it work. So perhaps there might be something mysterious there that we don't know. My take on it right now is that I haven't seen any evidence that consciousness is any more mysterious than, say, visual perception or something else, all of which we also don't really understand. So just because it seems mysterious and we don't understand it yet doesn't mean that it's not based on these mechanisms and won't emerge from it. I'm hoping that it will emerge from these mechanisms, and hopefully it won't take more than just predicting spike times properly. Maybe that's all it takes. Maybe we need more. Yes?
You mentioned that you gave this talk at the cathedral.
No, the Embodied books.
Adam Biggin.
Oh, sorry, Adam Biggin. Okay. Well, let's imagine that you gave the talk. Because the last question just prompted in my mind the God of the gaps. You know, what we don't understand is where God comes in. Have you ever had such a question from anyone in an audience?
Yeah, surprisingly, either almost never or never. I can't quite remember. I don't think I've ever really been asked this. I've never been asked a question that basically went directly towards dualism and towards what happens to the soul and things like that. I don't know if this is because it's still a very abstract topic, it's still difficult to explain, and it's something far removed from people's daily experiences, or if it's because religion doesn't see a problem with this. It might be that there is no problem with this because,
sees a problem with it, I can
you know,
tell you.
the basic. Oh, I don't know if that's true. For example, there's a transhumanist organization among Mormons. There's a Mormon transhumanist organization that loves the idea of uploading. And similarly, the Dalai Lama is a big fan of this project. In fact, there's going to be an address by the Dalai Lama at the 2045 Congress in New York next year. So it depends on your religion, first of all. And secondly, I think even Christian religions might be okay with it, because this idea that a mind or yourself could be substrate independent, could somehow still exist independent of the biology of your body, is really an intrinsic part of the religion itself. It's their way of coping with this problem of being and not being and all of that. And of course, whether we're allowed to make those kinds of things, and if that's dabbling with stuff, that's where it gets a little bit tricky. And it probably depends on people's personal views and fears and things like that. But yeah, I haven't really been confronted with it yet. But after you just had that question, and this is going to appear online in a video, probably yes.
I guess it depends if they're Catholic or Protestant or Muslim, then, doesn't it?
Ah, yes.
The brains that we create depends what religion
Oh, yes, okay, right, yeah. Right. Well, but maybe it depends on where those eventually go then. So, yeah.
You could also edit out those defects when you get in there.
Yes.
There's a God's in there somewhere, faction in the science fiction community. In science fiction conventions, this comes in certain panel discussions, and it seems to me that science fiction authors and writers could very well attend symposiums such as this because there's some great stories in there somewhere.
Yeah, I'm not sure if that was a question or a statement, but I certainly agree with the statement.
But the thing is that what we're looking at is personality upload, independent of the body. And I have a gut feeling that it isn't possible, but let's find out. Let's build the super intelligence, the artificial intelligence that's capable of looking at the problem, and then pose the question or give it the order, duplicate my self-awareness transort, and see what happens.
Yeah, this gut feeling seems to be something that happens a lot. But of course that happened a lot as well before we invented motorized heavier than air flight, where people had gut feelings that it was impossible to make something that would fly, and yet we did. So I think sometimes gut feelings are off. Are there any more questions?
Does anybody want to ask that?
There's one more in the back, I think.
Yeah. Okay, so if your consciousness or your personality is somehow contingent upon the fact that you are a kind of embodied being, does that mean that if you, given it's substrate independent, because your embodied nature changes, to what extent do you think that would impinge upon like a sort of a change in personality or a change in outlook or something like that?
I actually personally believe that embodiment is very important. I think that when we really say who we are, what we are, all of this stuff, it's not just what's being processed inside here, it's the interplay between everything that's going on. So I'm absolutely convinced that if you then change the way that you're receiving input and what kind of input it is, either because the new body that you have has senses that are slightly different, or because you're in a different kind of environment. Let's say, for example, that you're in a virtual reality rather than just put back into the world, and that reality happens to have different rules, or something else goes on there, that it's going to affect something about who you are and how you think. Just the same as when you're entering a different environment and a different circumstance now, like suddenly you're not here, but you're living in Afghanistan or something like that. It's going to change a bit about who you are too. The degree of change is important, and I think that's something that also comes up often, even at the basic question of can you do something like a whole brain emulation, what is the allowed error rate? How much can you get wrong in those measurements? And something that I think is a safe minimum, or is it a minimum, maximum? Well, we may be able to go above that. It may be possible to deal with more damage and more mistakes, but at a minimum, we could deal with the amount of difference or change that we go through from moment to moment anyhow. When cells die, so our systems change, learning changes what's going on inside of us. So there's an amount of change that goes on regularly that we're perfectly comfortable with. And below that level, any difference or change should be fine. Above that level, it's an experiment.
So
Yes, Marcus?
So you believe that embodiment is important, but virtual embodiment is sufficient. And if it's sufficient, and if the virtual reality is perfect or sufficiently close simulation of reality, would you then feel a difference, or do you believe that there would be any difference?
Okay, so I guess the first point was, do I think that embodiment, that is important, but that virtual embodiment is good, can be good enough? I do think that embodiment is good, and I personally see this not as a way of moving into virtual realities. I see this as a way of continuing to live in the rest of the universe where we don't have, an Earth environment. So I'm not only interested in virtual realities. But if you do create virtual realities, it's actually interesting to try different things and new things. That's one point. But yes, if you were to create one that is as close as possible to the reality we have now, and you could do that simply by measuring what kind of input we actually receive through all of our organs, including our skin. And if you could, at least for that input, recreate something that is very close approximation, then my assumption would be that it wouldn't really change much about how you feel and what you are, because, that is really our interaction with even this environment. It doesn't seem that there would be any other way for information to get in and out of us and how it would affect us. Yes, you.
I just want you were saying you can upload the mind to a computer, but what I wanted to ask, because subconscious plays a huge part in the decisions we make, and it depends on the neurons that's firing, etc. Now, with subconscious, how obviously it is, I'm guessing, it's a combination of memories, behaviours through childhood to the current point. Is that how is subconscious going to play in your upload of the mind, and how do you measure that?
Yeah. It's interesting that you're asking about subconscious when most people ask about consciousness, and how would consciousness ever get into this?
Well, because subconscious has a part in the decision making.
Yes, of course, as does everything else. Most of the stuff that goes on is subconscious, right? I'm not really conscious of how I'm turning all the light that's coming into my eyes that happens to make you appear in my mind. That's not something I'm doing consciously. That's all happening subconsciously. That is the basis of neural processing, is all this stuff that's happening on in parallel in there. That's what all those mechanisms are for, and that's exactly what these procedures are trying to capture, is what those mechanisms are, how they're all connected, what's happening at every millisecond as those processes are being carried out. So the subconscious, conscious, anything that's an emergent function of the biology of the brain, that's what we're trying to capture in there. And as long as you believe that in fact your mind is the consequence of that biological processing that's going on inside your brain, then yeah, this is a machine. It's something that you could reconstruct somewhere, and it would produce that emergent phenomenon.
So would that machine have all your memories of
Yes.
the past? And how would that calibrate all those memories that you have calibrated over how many years you've been alive and etc.?
That's why you need to capture all that data about the synapses that are there, how many of them, of which type.
From childhood and just
Well, the synapses in your brain, and it's not just synapses, there are whole different stages of memory and how they get established. But let's just say for a second that we're only talking about synaptic memory. That is exactly where your memories of everything that has caused you to be who you are right now is stored. That's your state.
I think I understand the question. So if you're first 30 years old and you start simulation,
Yeah.
will the person believe this virtual person that it's 30 years old? Yeah.
Yeah.
Or
Yes.
will they believe that it's just born? I think this
No, 30 years old. Yeah. Yeah. So was this really the last question, or should I take that question too?
Will there be ethical considerations with basically a form of locked-in syndrome where you will have the capacity to store and perhaps run this consciousness, but that you won't have ways to communicate with it? And to develop those ways to communicate with it, you're going to have to experiment. So is there going to be ethical considerations when you're developing these ways to communicate with the stored consciousness?
Absolutely. I'm sure there will be many ethical considerations, even if you're only dealing with a small part of the problem. So take for example the chip that Theodor Berger has developed. He's developed a small chip that replaces a piece of functionality in the hippocampus, and that he thinks could be used for cases where stroke has damaged the hippocampus. That's a small piece of this. It's basically how do you make something that works like a part of the brain, and then how do you interface it with the rest and get it to work? You'll have so many ethical considerations there. What happens if it doesn't work properly? What happens if people feel different afterwards? There's always going to be a stage of experimentation involved. But if this is the difference between life and death, then it's probably worthwhile to test and explore these opportunities, and I'm sure that you would find plenty of people who would say it's worth the risk for them personally.
I was mostly concerned about the boredom. If you're locked in, your consciousness is running, but you can't communicate to the outside world, you're blind, you're deaf.
Yeah, I think it would be kind of bad to create a whole brain emulation and not connect it to anything, but then still run it. I could imagine that perhaps you could put it into a dreaming state, as in you would just be asleep all the time and dreaming. But that's kind of a strange thing to do. Why would you build a recreation of your brain so that you could put it in a box with no input and no output?
Well, you need to develop the output starting with the brain that you'd uploaded. To test and to experiment these output methods, you'll need to have a lot of bored test subjects over time.
Someone will have to test it, of course, and I'm assuming you would test it with smaller brains like flies first before you get to it.
Okay, let's go. We have time for
It's time, so it's a short